Hello everyone. Let's analyze. We've learned what it means to be integrable, at least in the sense of Riemann, and we learned two classes of functions that are integrable: increasing and decreasing functions and continuous functions. Now, today we're going to talk about the arithmetic of the integral. So the five results we're going to talk about are results that are probably already familiar to you. In fact, for each result, you'll probably have an intuitive idea of why each is true, based on your understanding of the integral as an area. But we'll use the definition of the Riemann integral to prove rigorously each result here. So let's prove each result. Suppose f is Riemann integrable. Then, for any number alpha, alpha f is Riemann integrable, and the integral of alpha f is alpha times the integral of f. So the lower sum for some particular partition P is equal to the sum of rectangles whose heights are the infimum over each subpartition or subinterval times the width of the subinterval. Now, sorry, this is an alpha. This alpha can be factored out. And if I can factor it out, that means that this is equal to, or I can factor alpha all the way out, and what I'm left is just the lower sum of f. And notice that my partition P here is arbitrary. It's true for all partitions P. If it's true for all partitions P, then the supremum over P of the all lower sums of k times f for every partition P, that's alpha, is alpha times the supremum over P of the lower sum of f over P. And remember, this is the lower integral. Right? So this equality follows just by definition. This is the definition of the lower integral. And the lower integral, well, that just equals the integral. I know it equals the integral because f is Riemann integrable. And the definition of Riemann integrable is that the lower integral equals the upper integral, which equals the integral. Now, similarly, the infimum of the upper sums of alpha f over some partition P, right, for every partition, is alpha times the infimum of all upper sums for every possible partition, which by definition is alpha times the upper integral, because this is the definition of the upper integral, and that's equal to alpha times the integral. right? Since this is the same thing, this is the same thing. And this is the lower integral of alpha f, and this is the upper integral of alpha f. So we can conclude that the lower integral of alpha f equals the upper integral of alpha f, and both are equal to alpha times the integral of f. And we've proven our result. Next result. If f and g are both Riemann integrable, then f plus g is Riemann integrable, and so is f minus g. So let's prove the result. Let's consider the lower sum of f plus g over some particular partition P. It's equal to the sum of the infimum of f plus g. All right, so here I'm going to write the infimum of f plus g so that we can differentiate when I write the infimum of f and the infimum of g, which I'm going to need to show these results, times the width of my interval. Now, remember that when I say mj plus g, as I just mentioned, that is the infimum over the subinterval of f plus g, and that's greater than or equal to the infimum of f plus the infimum of g. That allows me to make f and g each as small as possible, rather than making their sum as small as possible. Which we would write that in our shorthand as little m of f plus little m of g. Well, that means that the lower sum of f plus g over p is greater than or equal to I'm going to write that same summation, except I know that this term is greater than this term. Which equals the lower sum of f and p plus the lower sum of g and p. And notice that my partition P here is arbitrary. So this implies that the lower sum of f plus g, which is the supremum over all p of all lower sums of f plus g, is greater than the supremum of the lower sums of f and g, respectively, summed up. Which equals, right, this is equal to the lower integral, but since f is integrable, this is equal to the actual integral. Now, we can follow that same line of reasoning for the upper sum. Right? So similarly, the upper sum of f plus g for a partition P is less than or equal to the upper sum of fp plus the upper sum of g for the same partition. Again, for the same reason, because my partition here is arbitrary, the infimum of the upper sums, which is by definition the lower integral of f plus g, is less than or equal to the infimum of the upper sum of f plus the infimum over all upper sums of g for every partition P, which equals, oh, sorry, that's a mistake there. That should be upper integral. Right? This equals the upper integral of f, which is just equal to the integral of f because f is integrable. So, I claim that this proves our result. But I don't blame you if you don't see it right off the bat. Let's put all the pieces together. The lower sum, written here, of f plus g, we know from one of the lemmas we proved in a previous lecture, is less than or equal to the upper sum of f plus g, and the upper sum is less than or equal to the integral of f plus the integral of g, and the lower sum, seen here, is greater than or equal to, well, that same summation. So because the lower sum is less than or equal to the upper sum, but both of them are bounded below and above respectively by the same number, they must be equal. Therefore, the lower sum equals the upper sum, which equals the integral of f plus the integral of g. We've proven our result. Of course, you might say, well, wait a second. I was promised a minus. I don't see a minus. Where's my minus? Well, f minus g is f plus negative 1 times g. And the integral of f plus negative 1 times g is the integral of f plus the integral of negative 1 times g. And from our previous result, the integral of negative 1 times g is negative the integral of g. So f plus negative integral of g is just f minus the integral of f minus the integral of g. In other words, the minus follows by just putting together our two results and letting the constant be -1. If f and g are both integrable, and f is less than or equal to g on my closed interval a to b, then the integral of f is less than or equal to the integral of g. So let's prove this. Right, and again, I would urge you to take a second and understand intuitively why this is true if you don't already. Right? If f is less than g, then the area under the curve of f ought to be less than the area under the curve of g. In fact, it would be a good exercise to draw a picture illustrating this idea. If f of x is less than g of x for all x in my interval, right, which is the hypothesis of my theorem, then the infimum of f which is by definition, well, the infimum over the jth partition or subinterval is less than or equal to the infimum of g over the same subinterval. And this subinterval is an arbitrary subinterval of an arbitrary partition. It follows that the lower sum, which remember is the sum of rectangular areas whose heights are given here, is less than or equal to the lower sum of g, right? Which is the sum of rectangles with the same width but bigger or equal heights. And since this is true for every partition, it's also true for the supremum of both sides. This means the supremum of L, which is the lower integral, is less than or equal to the supremum of the lower sums, which is the lower integral. Right? Remember, this is just the supremum of all the lower sums for every partition. This is the supremum of all lower sums of g for every partition. And since f and g are both integrable, this is just equal to the integral. And that gives us exactly the result that we want. Right, by the way, hopefully you'll forgive my shorthand. This is the integral of a to b of f of x dx. Right? We've proven exactly what we sought to prove. Next, if f is Riemann integrable on a to b and b to c, then f is Riemann integrable on a to c. Just to give you an idea, again, because hopefully this makes intuitive sense, I have the integral a, or the interval a to b and b to c, right? If I take the union of these two, I get this. And so this is integrable, and so is this. So if I just sum this area plus this area, I get the area under the curve all the way from a to c. Again, these are results that we already know, that we understand, that make perfect sense to us geometrically, but now we're going to prove rigorously using the definition of Riemann integration. So let P be a partition of A to B, and let Q be a partition of B to C, right? So P partitions this interval and Q partitions this interval. Well, if I take the union of these partitions, in other words, if I put this partition together with this partition, I've partitioned A to C. Therefore, if I were to look at the lower sums of F over the union of these partitions, well, right, I would be summing these rectangular areas plus these rectangular areas. So let's consider every such partition. That is, let's consider every lower sum over a partition that's assembled by taking a union of a partition of A to B, this interval, and Q is a partition of B to C, right? So this is a particular kind of partition, right? It's essentially, I'm saying consider every partition of A to C where B is one of the partition points. That's essentially what I'm saying, because, right, B has to be xn of P and the first partition point of Q. Right there, it's the point that these two partitions have in common. Right, remember, P is a set of finite increasing points from A to B. Q is a set of increasing finite points from B to C. P includes A and B. Q includes B and C. Well, that's a particular kind of partition, but it is a partition of A to C. So if I take all such lower sums, well, that's a subset of all lower sums. Let's make this R, right, to not confuse. So R is just any old partition. Any old partition of A to C, here to here. All right, so R is a partition of A to C, doesn't necessarily include the point B. Now remember, every element of this set is equal to a lower sum of F and a lower sum of F for partition P and a lower sum of F for partition Q. Remember, P partitions A to B, Q partitions B to C. So if I were to take the supremum of this set, right, it would be less than or equal to the supremum of this plus the supremum of this. But because it's contained in here, this supremum would be even bigger. In other words, the supremum over P of the lower sums plus the supremum over q of the lower sums has to be less than or equal to the supremum of r of all lower sums. Right, because R allows me to consider any partition of A to C. Now remember, P is a partition of A to B. The supremum of all lower sums equals the lower integral of f from A to B, and f is Riemann integrable on A to B. Right, that's in our hypothesis. F is Riemann integrable on A to B. So this equals, well, by definition, the lower integral of f from A to B, but since f is integrable, that's just equal to the integral from A to B. And this term here is equal to the integral of f on B to C. Now, for similar reasons, right, for the exact same argument, the infimum of all upper sums for every partition A to C is less than or equal to the integral from A to B of f plus the integral from B to C of f. Now, remember that the infimum of all upper sums is greater than or equal to the supremum of all lower sums. This is the upper integral. This is the lower integral. This is greater than this. But this is bounded below by the same thing this is bounded above by, meaning that they're equal. So we have our result. The lower integral must equal the upper integral. And if they're equal, I'm sorry, this should be 2c. And because they're bounded above and below by the same thing, they must be equal to that bound, which is the integral from A to B plus the integral from B to C of f. And we have proven our result. So I would encourage you to make sure that you understand the ideas here. If this is your first time seeing Riemann integration, then it's not likely that in just a single run-through, everything is going to make crystal clear sense. Okay? You may have to pause, watch again, pause, write out the ideas for yourself, draw pictures, and perhaps most importantly, come by office hours. Ask questions. I'd be more than happy to talk integration with you. And now we've come to the triangle inequality for integrals. And know that it's really two results. It says if f is integrable, then so is its absolute value. And the integral of the absolute value is a upper bound of the absolute value of the integral of f. Right, which is the only thing we're assuming at the beginning to be integrable. Right, we need to prove that this number actually exists, and then we need to prove the inequality. Okay, so proof: f is integrable implies that for any epsilon greater than 0, there exists a partition P of A to B for which the upper sum minus the lower sum is less than epsilon. I remember what the upper sum is, right? The upper sum is the sum of rectangles whose heights are the supremums of f in each subinterval. The lower sum is a sum of rectangles with the same width, but the heights are the infimum of f in a subinterval. This statement can be rewritten as a sum of differences of heights. Right? So this is equal to this, which is less than epsilon. So our first goal, goal 1, show that for the same epsilon, I get the same result for the absolute value of f. Now again, this is equal to the supremum of the absolute value of f minus the infimum of the absolute value of f times the width. Now, if we can show that this summation is less than this summation, which we know is less than epsilon, we're done. And if I look at the summation, each term has a common number in the product, right? Each term is a product, and the delta xj are both positive numbers and the same. So really what I need to show is for each j, this is greater than this, right? In other words, my goal is met if mj of f minus little mj of the absolute value of f is less than or equal to that. In other words, the supremum of the absolute value minus the infimum of the absolute value over a subinterval is less than or equal to the supremum of just f minus the infimum of just f over the subinterval. And I need to show this for each j, 0, 1, 2, all the way through n minus 1. Right? So this is what I want to show. If this is true, this is less than this, which is strictly less than epsilon. Okay, so let's set upon our goal. Again, for each j, And for any x and y in my subinterval, the absolute value of the difference is less than or equal to the absolute value of the difference of just plain f without absolute values around here. This is the reverse triangle inequality. Right, so this result just follows by the reverse triangle inequality. And this says, right, how big can f of x be from f of y if x and y are within an interval? Well, the biggest apart this can possibly be is the supremum minus the infimum. Right, that's the biggest it could possibly be. It follows then that the absolute value of f of x is less than or equal to mj of f, or big MJ minus little mj, the supremum minus the infimum, plus the absolute value of f of y. And notice that x and y are arbitrary values in my subinterval. So this is true even if I take the supremum over the subinterval, because it's true for every x. And since it's true for every y, it's true if I take the smallest. Now remember, this is, right, our shorthand for that is big MJ of the absolute value of f is less than or equal to mj of f minus little mj of f plus little mj of the absolute value of f. Right, this is just a rewriting of this using our notation for supremum and infimum on a subinterval. Right, so this is just using our standard agreed upon shorthand. And when I say agreed upon, I mean instilled upon by my dictatorial rule. Therefore, if I subtract this from both sides, I get the exact inequality I sought after. Right, remember, my goal is met if this is less than or equal to this, and that's precisely what I just shown. In other words, the upper sum of f for p minus the lower sum of the absolute value of f for p. Remember, p is the partition that satisfies the epsilon bound for the upper sum and the lower sum of plane f, which by hypothesis is less than epsilon, right? Because such a partition that gives me this epsilon condition is met by the fact that f is integrable. And this is less than this because each term in the summation that these represents is less than each term in the summation that this represents. And we've proven our first result, right? So, in other words, result 1, check. Now, the next result is the actual triangle inequality, which I claim is already met. I can see you don't believe me. You can see it in your eyes. Well, let me show you. F is less than or equal to its absolute value, and it's greater than or equal to its negative absolute value. That implies, by the preservation of inequalities for integrals, which we proved just a few minutes ago, that if I were to integrate this, this, and this, these inequalities are preserved. This is equivalent to saying the absolute value of this middle term is less than or equal to this number. And now we've proven the complete result. And now we come to a fundamental result, the Fundamental Theorem of Calculus, typically the punchline of your Calculus 1 class, and the link between the antiderivative and the integral. Suppose that f is continuous, then f has an antiderivative, and the integral of f on the closed interval a to b is the difference of its antiderivative evaluated at b and a for any antiderivative f. So let's prove the result. So first let's build a function. Let big F map the closed interval a to b to R, be defined by the integral from a to x of f of y dy. Just so that we're clear about what f of x is, if this is a and this is x, and that curve is little f of y, and by the way, y is the variable that ranges from a to b with x in between, then f of x is the area under the curve, right? F of x is this entire area. Right, if x is fixed, this is just a regular definite integral, but as x changes, the area under the curve changes. In other words, I get a different number, which is the exact definition of a function. It maps a number x to another number, right? It maps a limit of the integral to a area. By the way, how do I know that this number exists? Well, because I'm assuming that f is continuous here, which means it's integrable. Now I claim that f prime of x equals f of x. Right? In other words, I'm making the claim that big F is in fact my antiderivative of little f, because I'm claiming that the derivative of my potential antiderivative of little f is little f. Now, let's consider the definition of the derivative. If you forgot, it is the limit of secant slope as the width of the secant goes to 0. So, my secant slope, right, is rise over run, and my run is h. And of course, eventually I'm going to take the limit as h goes to 0. Well, this equals, right, remember this is f of x. If I were to extend x to x plus h, then f of x plus h minus f of x, that's just this area here. Right? This numerator is given by that red area. So I get 1 over h times the numerator. The integral from x to x plus h f of y dy. Now, by the way, I am assuming here that h is positive, right, by the way I wrote my integral, which means I'm actually going to take a limit from the right, but that's okay, we can also take a limit from the left as well. Now, the fact that f is continuous on a closed interval, right, meaning that it is compact because it's closed and bounded. You remember Hein-Burrell, don't you? Then f is uniformly continuous. Meaning that for any epsilon greater than 0, there exists a delta greater than 0, such that if x and y are in the interval a to b, and x minus y in absolute value is less than delta, then f of x minus f of y is less than epsilon, right, just by the definition of uniform continuity. Now, by the way, remember that if I were to take the limit as h goes to 0 of this secant slope, right, that is this rise over run, right, that's a slope, I'm claiming that I'm going to get f of x. In other words, if h is small enough, this minus little f of x is less than epsilon. So let's take a look at that difference. Right, remember that this is equal to this, f of y minus h dy minus f of x. Now again, I want this to be less than epsilon if h is small enough. Well, what do I need h to be smaller than? Well, let's find out. This equals right, because this f of x is constant with respect to the variable of integration. I can write this. Now let's just stop a second and make sure that we understand why I'm allowed to write this in this equality. Well, this is constant. So if I were to integrate this constant from x to x plus h, the area under the curve, right, because it's not a function of y, would just be exactly the area of a rectangle. It would be f of x times h. So if I were to take that integral and divide by h, I would just get f of x, and that's why this is equal to that. Now, if h is less than delta, then f of y minus f of x, an absolute value, is less than epsilon. Which means, first let's apply the triangle inequality. Right, so this numerator is strictly less than epsilon. And this equals, now here, my integrand is constant. So I just get x plus h minus x, which is h. So I get epsilon over h times h, which equals epsilon. Therefore, I show that if h is small enough, this difference is less than epsilon. So that implies that the limit from the right of f of x plus h minus big F of x over h equals f of x, little f of x. Similarly, we can show, using the exact same arguments, that the limit from the left of my secant slope is also f of x. And because the limit from the right and the limit from the left agree, the limit in general exists, which means f prime of x equals right, by definition of the derivative, rise over run of a secant line, and that's f of x. Furthermore, f of b is the integral from a to b of f of x dx by construction. And I can subtract from that f of a because f of a is 0. How do I know f of a is 0? Well, f of a is, if I remember the definition, right, because I constructed f of x, f of a is the integral from a to a, which is 0. Technically, that's a improper integral, but we'll get more into that later. Now, I constructed f. F is a particular antiderivative. In fact, it's the antiderivative that is 0 at a, which, by the way, it's useful. Sometimes we want a very specific antiderivative, and that construction allows us to do that. But what about any other antiderivative, right? For any other antiderivative, g, we know that it's just f plus a constant. Therefore, g of b minus g of a is f of b plus c minus f of a minus c, and my c's cancel. And this is just equal to the definite integral a to b. So, in fact, this difference works no matter which antiderivative I pick, and we have now proven the fundamental theorem of calculus. That's it for now.